Recording. Okay, sorry for the delay. I'm busy just logging in so I can pull up our. Actually, I don't really even need to log in, but your exam is tomorrow. So if you are sick, I've already got an email from at least one student saying, "Hey, I am really sick." So if you are sick, again, just simply send me a message and we'll arrange with your TA as to when you can make up that exam. Okay. Again, you get a cheat sheet front and back. The exam is on paper. Okay. And the format is going to be very similar as I went over on Thursday. But here we'll finally go over the answers. So that is what we'll be doing today. Continue and restart. Sure. Just need. Okay. So, first question is, so again, over here, there's going to be stuff, and I was a bit more explicit with the exam that I printed out here, by the way, that basically this string dot starts with is something you'll want. It's here for reference. I even mentioned in the exam to go back here and reference it for one of our problems. So that'll be nice and useful. Okay? So, exam 1 review. Okay, great. Here we go. Sorry, I'm just making sure that this runs. Okay, yes, exclude folders, whatever. Run. Okay. So, first problem is a doubly linked list. Assume every node has a variable storing their memory location, denoted by the letter. Okay. For each of the following questions, indicate which of these is the case. So here we've got D. Previous, next, previous. So we just basically are going to go forward and back until we see them. So this should be, basically some freebies. D.previous, next, previous would be B. C.next, previous. C.next would be D. Previous would be also B. And then this one B is B, sorry, 1 second, zoom F11 so we can see everything. So B.next, prev is also B. They're all B because I'm that kind of professor. I have done a series of 5 true-false questions in 1051 in the past where all the answers were true. I am that professor. Statistically speaking, it'd be weird if you never got one of those. Okay? That being said, I generally try to avoid that kind of fake out on actual exams because it makes students panic. So, write a sequence of commands that will remove the tail of a doubly linked list. Okay, let me just double check that this is working. Okay, so to remove a tail of a doubly linked list, right, that is... So to remove the tail, that's removing the last index. So basically what we would need to do is, but because we're working in a doubly linked list, this isn't too bad. We would say that tail is equal to tail dot previous to get the previous tail. Okay? Sorry, the item that's in front of the tail. This will make more sense as I draw it. Actually, why not draw it in advance? Okay, so here we it just so happens that we've got 3 nodes, right? Boop, 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 boop. Okay, and next. What are we going to do? Draw what happens as each line executes. So we initially have this as the tail. This is, I'm going to put H for head, but we really don't need that. First thing we're going to do is step 1. Okay, I guess I need to wake up. Okay. Step 1, we go ahead and make this the tail. And then step 2, what I'm going to do is have this point to null, which I can represent with just a box with an X through it, or I could represent it with the word null. And then this will get garbage collected. You can, I just don't have the fidelity to do this in multiple steps here. So try to be as good as I could. But really, first thing we do is we set tail is equal to tail.previous, and then the next part is saying tail.next is equal to null. And then I suppose we should also say size minus minus, technically speaking. But the reason we do the tail.next is equal to null is as long as tail.next is equal to what we had over here, it's just going to exist and still take up memory. What we have to do is say tail.next is equal to null for it to get garbage collected. Remember, if you have some kind of thing, okay, as long as there's a variable or some kind of reference to this thing being stored somewhere, then Java says, aha, this is being used, don't get rid of it. As soon as all the references to it are gone, Java goes, oh, well, the only thing keeping track of it is me now, so I guess I'm going to delete it. And that's how that works. Add item 0 to a new linked list. So here we go, boom, boom, boom. So we've got doubly linked list over here. Let's try to be a bit more drawing good thing. Okay. So we've got our head. We really don't need to worry about the tail here. 1, we create a new node. Okay. 1, create a new node. That will be, and I'll call it adding, right? We create a new node called adding. Step 2, oh, come on. Let me draw in this. What? Wow. Okay, that it considers that all drawing. Step 2. Okay. I guess this is why we have the whiteboard. Okay, because it doesn't act all stupid. Okay. Step 1. We have 3 linked lists, and now they're rainbow colored. Cool. I too love crayon. Okay. We have our head with my terrible handwriting. Step 1 is, whoops, no, this is head over here. Step 1, we make our new node. Okay. Step 2 is connect. Step 3, connect that. Step 4, make this the new head. Oh my gosh, my finger writing is terrible. Okay, and so now that I've drawn that out, I can actually answer this question a bit better, which is to say, hey, sequence of commands, node E adding is equal to new node to create our first node. Okay. Next, we want to say adding dot next is equal to head. Head dot previous is equal to adding. So basically, what I'm doing is I'm connecting the new node to the head, put it in front. And since it's doubly linked, I'm going to go backwards with the head dot previous is equal to adding. And then finally, I'm going to say, hey, the new head is equal to adding. So this stores the memory location of adding in the head, meaning that now the beginning part of the beginning of this list will be the head. Size plus plus at the end, but honestly, if you forget to put size plus plus, I'm probably not going to count off. It's just, I try to be as correct as possible. I'm going to try to move quickly. If you can't get this down, that's why I'm making the recording. So, all right. This one is not too bad, right? Suppose you have some list of integers. This one's the easy one. This one, think of this one as a warm-up. Also note that it's only 5 points. Okay, write a method that finds the minimum and maximum values stored in the list and returns their sum, regardless of the implementation of the list. All right. So this is both going to be very easy, but the next question is actually going to be hard, kind of. And so what we're going to do is I'm going to show you, and I'm going to be very nice and mention that the question 9, the what's the value, is probably your best bet for extra credit on this. Okay? So let me go ahead and copy this in. Find the minimum and maximum values. Now, I did implement this in a very, very peculiar way, in my opinion. Normally not as peculiar as I would, this is not as peculiar as would normally do it. Okay. Okay. Wow. Void main. What is this nonsense? With Java. What in the world? Where's my class? Do I not need a class anymore? Interesting. New. Java class. Array list probs. Or actually, I'm going to call this lab2 probs because I'm priming you to think, oh, it's array lists. This also does, but less so. And here we go. Fascinating. Things I learn about Java, which are new. They always do try to make programming languages easier to use. So list. So here we're taking a list of this, public, and return. This is the difference between, this is the sum, max, plus, min. Now, the reason I did this is that integer.maxValue is that I didn't want to auto give you part of the problem, which is more efficient to do, which is list.getZero, assuming the first thing in the list is the item. I didn't want to give you the get, so I had to set it at sane values. The sane values are, well, anything in this list is guaranteed to be less than or equal to the biggest number there is. And anything in the list is guaranteed to be bigger than or equal to the smallest value in the list. So that's why the min gets the max value, the min, and the max gets the min value. Okay? So now we could do this with a for each loop, but I'm not going to. I'm going to use for reasons that will be apparent. But you could just essentially do the following thing. You could do for integer I in, I'll go num in list, and then proceed to do the problem from there. I'm not going to. For I is equal to 0, I is less than list.size. Okay? And now, we don't need to do another for. I'm going to say int num is equal to list.getI. And I'm doing it this way so that you can just simply replace it with a for each easily if we needed to. Okay? So now it's actually very straightforward. Whoops. Oh man, I really messed up the code there. Boop. Boop. I was accidentally holding down control while I was doing things. So if num, there's no trick here. If num is less than min, min is equal to the new number, and we don't need a second for loop. We can just ask, it's what some students will do, but you don't need it. It's not really going to affect the runtime. If max is greater than, if num is greater than max, then that max is the number. That number becomes the new max. That's it. Okay, and again, if for each loop, all you would do is replace the for each loop with these. You'd replace these two lines with the for each loop. Now, the reason I did it this way is this question over here. What is the time complexity of this algorithm? Now, if you do the for each loop, that's very easy. For each number, get the for each number, check if that number is less than or greater than. That takes one operation per number, well, two operations per number, so it ends up being O of n. On the other hand, if you implement it like this, and you assume it's an array list, I will also assume it's an array list, and that will be, and this takes O of n time because this is an O of n operation. However, if it's a linked list, this operation takes O of n time. So it takes, you have to seek to that position. So you get costs 1, then 2, then 3, then 4, then 5, then 6, then 7. So this becomes an O of n squared algorithm using a linked list. If you're using the, if you're using a regular for loop. A for each loop will just simply save its position as it's iterating through the list. If you've checked out the homework, right, you'll see how that iterator works as it basically saves where it is. That's why the iterator exists, so you can do these efficient iterations through things like linked list, and they don't, you don't have to seek, sorry, you don't have to waste time seeking to where you've already been. Make sense? If I were to say that there was a route for extra credit, it would probably be, if we're getting that, extra points for exceptional answers, it would probably be over here. Just make sure you're correct about what your answers are, When in doubt, though, we will assume that you can always say, assuming array list, and then put this over there. And if you don't mention you're assuming an array list or a linked list, I'll just assume it's an array list because Lab 2 is all about array lists. So you're primed to think of these as array lists. Anyway. Now, suppose you have some list of string. Write a method, reverse words, that takes in that returns a new list with all the strings reversed. Okay? And to be clear, I do try, and I do give these examples, in outs, because otherwise I might get a student who thinks that you can read that, and while you're quickly reading and working in a stressful environment, you might think, oh, reverse the list. So it should be nice world hello, right? As opposed to ole, drow, and ekin. So what we're going to do is they said we want to return a new list. So let's go ahead and start by creating that new list to return. List string I'm going to just call it output is equal to new, and I'm going to create it as an array list because why not? You could totally do a linked list here. Will that change the runtime? We'll find out. This won't. This probably won't if we do it the way. So this time I'm just going to do a for each loop just to be different. For string word in list, right? I need to basically reverse the word, okay? I'm just going to do that as a function here. String reversed is equal to, and I know that function doesn't exist. I'm just doing it as a placeholder right now, right? But we reverse the word, then we just simply do output dot add reversed, and that's it, right? Basically, we just got to figure out how to reverse the word, but once we do so, we add it, okay? Now, if you leave it like this, thinking there's a reverse function, I'm actually going to probably just give you like 7 out of 10 on that because the vast majority of the problem is done. You wouldn't be too remiss in thinking, oh, there should be a reverse or a reversed function, right? Because Python has a reversed function. And string builder, as opposed to string, does have a reversed function. But, right, string builder, but you don't know about string builder or like, okay, let's see. I hate doing things like this, but I'm just going to do it because I want to show the method call. Yes, you can like totally make an anonymous function like this and do, like that will, like that, whoops. Here, this is like a one-liner for it, but like, is it reverse? Okay, oh, and then dot toString, right? That would do it, but you don't know to do that. You haven't had to mess with string builders, right? And that looks god-awful besides, right? So that's part of the reason why I wouldn't necessarily hit you too hard for thinking, oh, there's a simple way to do it in Python, like in Python, okay? We do have a couple ways to go through this, though. Okay, but the way we need to do this is basically a for loop. So string, especially in an exam when we don't necessarily remember. So string reversed, okay, and then what we're going to do is we're going to add that to our output. So what we're going to do is we have a few ways of doing this. First we could do a character at loop, like for I is equal to 0, and then we would rely off of word dot car at, right, to iterate through. Make sense? And add those in reverse. Okay? I'm just going to briefly allude to that solution. The other way we can do this is you might want to try to do, because you're into these loops right now, car C in Word, right? And this does not work. I'll fix this error in just a second. I actually wouldn't ding you too hard for doing this in an exam. I'd probably take off 1 point, if that, if the next part was correct, which is reversed, right? Typically what you would do is that if you were copying a string, you'd do reversed is plus equals C, which is the same as saying reversed is equal to verse plus C. So basically for every letter, add it to the end, and that gets you an exact copy, right? If our word was wolf, we would add W, then O, then L, then E, right? All to the end. Sorry, done this way for you guys, right? It would be, let's add W, then O, then L, then E. So F, why E? Okay. But if we want to reverse it, it's actually pretty trivial to do. What we do is we put the character first, as opposed to like setting up, and you can do this instead of setting up an iteration that goes backwards with the char at as well. So reversed is equal to C plus the word. And if our word was wolf, we would put W on the beginning, then we would put O at the beginning, then we put L at the beginning, then we put F at the beginning, thus reversing wolf into flow. Make sense? So now about this. This makes sense because if you're coming from Python, it makes sense that you should be able to do a for each loop over a string. You can do that in Python because Python is great. So why can't you do that here? Because strings are not iterable for some reason. To amend this issue, for some reason, you just put dot to character array, turning the string into its much more primitive format of being a character array, because that's what a string is. It's an array of characters with extra functionality added on top to make it easier to work with. And arrays are iterable. So this works. It's stupid. But if you forget this 2-character array on an exam, I'm honestly probably not going to care unless at the end of the day. And if I do on a 10-point question, it's going to be worth 1 point of caring. The way I do try to, so a bit of guidance about how I grade. All right. I try to view questions, especially ones that are 10 or more, as though if they were the entirety of the test. So a 9 out of 10 would be an A for a question, right? That makes sense? So this, if you mess this up, right? Especially or something minor that's super easy for anybody working with an IDE to correct, I'm gonna basically ding you a point, give you a 9 out of 10, which is an A on the question, and so 8 out of 10 would be a B answer, and a C answer would be 7 out of 10. Okay? So on a more practical way of kind of grading, if your answer is mostly correct, I start at 10 points out of 10 and then deduct for the minor mistakes or for the parts you're missing. If, however, your answer is mostly wrong but has elements of correctness in it, I start at 0 and add for those elements of correctness. And that's assuming I don't have a rubric, and for a lot of these things I do have a rubric. But generally speaking, if like you have broken my rubric in some way or form, that is my secondary kind of backup method. Okay. Now, okay, time complexity of this algorithm. So it would be O of n, and just the justification for that is if you consider every letter to be a string. Sorry, if you consider n to be the number of characters, every character gets accessed once. There is something to be said about this over here, string plus word, but you don't really know about that, which is that doing string concatenation like this is expensive because we're generating a new string. That's why things like string builder exist, but again, you don't know about that, and once you do, it's a trivial operation to replace. I mean, it's even suggesting it over here. It's even suggesting it over here. That's why I don't even bother kind of with it. So if you're going for optimization, it's such a commonly thing. It's just a common thing, such a common thing to optimize that the compiler knows that doing this is bad news. So you can just assume that this is O of n over here. We're not trying to get too technical into the details, but I do try to let you know about these things. Right? You're still learning. All right. Delete list. New text, delete this. Okay. So deleting the list has a number of ways we could do this. If it's a doubly linked list, it's a bit weird though, because we do run into a problem if we set head. I was thinking about this with the student. After a student asked me, if I've got a doubly linked list and I just simply set the head and tails to null, we do run into a bit of a memory leak issue. Memory leaks are basically where things are deleted, but they don't actually get garbage collected. Okay, that's basically memory leaking in Java, where we just have something that where you destroy any reference you have to it, but doesn't get garbage collected. And if we remove the fact that you've got a head and tail here, this technically sticks around, I believe, unless they've changed how smart Java is about implementing these things, because each of these nodes contains is referenced by at least one other node. So they're all storing each other and all keeping each other from being, deleted from memory. So to do this properly, what we need to do is essentially a while loop. And when we're iterating through a linked list, essentially, you want to basically do while node. Basically, let's go with while head is not equal to null. You either want to do while your current thing is not equal to null, or it's head. So while the current thing we're looking at is not equal to null, or current.next is not equal to null, depending on what you're possibly running into. So what we're going to do is we're going to say, while the head is not equal to null, head.previous is equal to null. So say, hey, the thing behind me doesn't exist anymore. And then I'm going to say head is equal to head.next. Head is equal to head.next. And yeah, that should work. With what I know about garbage collection. And then we set head. This will stop when head is equal to null. Set tail equal to null at the end. And then set the size equal to 0. Now, why does this work? Okay. What we're going to do is that while head is not equal to null, so wherever we are in the list, we'll say, hey, the previous thing doesn't exist. So it will no longer have any variables pointing to it, so it will eventually get garbage collected. And then when I say head is equal to head.next, right, once the thing before it gets garbage collected, nothing's going to point to the previous head. So now it's turn to get garbage collected. So as it moves on from that, it is now becomes a valid target for garbage collection. Tail dot is equal to null, basically says the last one's valid for garbage collection. And size equal to 0 is just to basically make sure that our logic is consistent. Okay. This one is, these first two problems are, this one's, I think, a bit actually easy, harder than 3 points would allow for, because it does require that thinking. This one's definitely a warm-up question. On the exam, expect something along the lines of these two questions, or these three. Okay. Okay, count is definitely a good warm-up, though. Okay. So, right. So for this, and this is part of the reason why I do it on paper, is because if you wanted to do it as by typing, you'd have to create your own classes to work on them. So I'm just going to call this LL exam, which is for linklist.exam, and I'm not even going to bother adding our methods over here. This it's just a linked list exam method, and it is going to have a public class node it's going to take an node e item node dot, and you don't need to put any of this in your answer. This is just so that I can do it. Node e next. I'm just going to do this one as a regular linked list. So, because we won't need the previous. And a lot of these where even if it's a doubly linked list, we aren't going to need the previous. Okay, but let's go ahead. You know what? Actually, though, I did say previous, so I'm going to go ahead and previous. But my plan is to use the previous as little as possible. All right, so public int count returns. We are counting the number of occurrences this item has. Int total is equal to 0. We are going to return this at the end, right? But we want to count the number of times that this occurs in our list. We need two more things. We need a node e head. Sorry, three more things. Node e tail. Node. I'm sorry, int size. Right? And the default constructor will set those to null and 0, so it's fine. And we can just assume that that everything else is in there because, again, we're working on this method. Because on a paper exam, you'd just be working on this. But this is just the only reason I did all this stuff was to make sure that it wouldn't throw red errors at me. I shouldn't get red errors on. Okay, so that was the entire reason for that aside. Let's go ahead and move this to the top. Okay. View. Hold on a second. Appearance. Distraction-free mode? Nah. View. I think what it is view and appearance. Zen mode is actually pretty nice. There we go. That'll work pretty well for this. Yeah, everybody can see. Do people in the back see, by the way? Okay. Okay. Total is equal to total. So like I said, I'm going to start out by creating a node e current. This is typically how you want to iterate through linked lists. You set a current node, and you set that equal to the head. Okay? Because you don't really want to adjust the head unless you're working with a method that you're literally going to be adjusting the head. So if you want to iterate through and find stuff, you set up current. And then you're going to be iterating using one of two techniques, which is, as I was saying, current, while current is not equal to null. Okay, that's your first way of doing things. The other way, which we'll see in another one, is while current dot next not equal to null. So when do you want to use one versus the other? You use this when the only thing you're checking is the current node you are on. Okay? So if I'm checking this one and then I go to the next one and then go to the next one and go to the next one. And you iterate and you basically you do your task and then you end with current dot next. You end with current is equal to current dot next. And you, okay, so that's one way to do that. And then the other one is you do current is equal to current dot next on this one. If current dot next is not equal to null, what this one does says, hey, I want to compare what I have. I either want to check the item after current instead of the item where I currently am. Okay. Typically, like if we're adding stuff in between current and current.next. Or if I'm comparing current with the one after it, right? So if I'm comparing pairwise or something like that. You want to use a while loop because the for loop's just going to look ugly as sin. And the for loop would look something like this. For current is equal to head. Current is not equal to null. Current is equal to current dot next. And I'm just going to put that on top. I'm just going to put this over here so you can see that's valid. It looks ugly as sin, because that's not how you're supposed to do for loops, right? But you can. This is one of those instances of your scientists were so preoccupied whether they could, they didn't stop to think whether they should, you know. For loops are pretty, you get used to the fact that you can put whatever the heck you want in these statements, okay? Anyway. So for this one, since we're just counting stuff, we're just counting the current items, so this is the only thing we need. So what we're going to do is, you might do like this, which is just checking to say, hey, if current dot item double equals, and I'll fix that in a second, equal to the item that I'm looking for, total plus plus. This one's actually fairly easy to do because that's all we have to do. I just wanted to talk about that iteration in a way where the problem wasn't too advanced, right? Now, here is the thing, right? Technically what we should do, if you do this on an exam, whatever, technically what you should be doing is a dot equals over here to check if two things are equal, right? That is what's the correct way to do things is. Okay. Time complexity. We check each item and then we advance. So these are all constant time operations. We're assuming checking for equality is a constant time. So we take O of n because we check every node and the item in each node once. All right. Public static, right over here, linked list, merge these items, right? So these are list A and list B are given to us as linked lists. We don't ever actually have to touch the head since we're going to assume that these are linked lists. The only reason I didn't explicitly put in linked list is because you can see how long the line is already. That would have made it go off screen if I had said linked list integer merge linked list integer, right? Everybody see that the only reason I didn't do that was because typesetting issues. So we're allowed to access the nodes, play with whatever. Sorry, it says static. You cannot access the nodes. You're allowed to remove, right, static methods outside of linked lists. So yeah, we don't have access to head or tail. That's great. We don't need it. And you're allowed to remove items from list A and list B. Now this one is one of the ones where you would find it about as difficult, on the same difficulty as the exam. What I like about this one is that this is actually, if you've heard of merge sort, this is the merge step of merge sort. So merge sort, and this is going to kind of give the second part of the answer away here. Merge sort takes advantage of the fact that if we want to take two sorted lists and merge them into one sorted list, that is an O of n time operation. You only have to do O of n comparisons. You don't have to compare all items to all other items. Okay? And the reason being is if we basically draw it out, I'm going to go 1, 2. I'm going to do 1, 2, and then I'm going to do 3, 5, 4. So 1, 2, 3, 4, 5, 7, and then 6, and then 7, 8, 9. So these are basically the same size. I'll right? Yeah, I'm off by 1, but oh well. Okay. So these are relatively the same size. Okay, just one has an odd number of items. Okay, to merge these two lists into one sorted list does not take a lot of work because they're already sorted. So we already know that the item at the front of each list is the smallest item of that list. So if I compare these two items with each other, 1 and 3, I know if this front item is smaller, then it's smaller than everything in this list because it's smaller than the smallest item. Similarly, if this item is smaller than all the items over here, then this is the smallest item overall because it's smaller than the smallest item over here. Make sense? So so once you see this algorithm, it makes a lot more sense, but we're just going to use this fact. Okay? So what I'm going to do is while one of these is not empty, I'm going to do the following. Which is smaller, 1 or 3? I'm going to compare the first items in the list. 1 is smaller, so I'm going to remove that and add it to my output. Which of these is smaller, 2 or 3? 2 is smaller, so I'm going to delete that, add it to my output. Which is smaller, 3 or 4? 3 is, so I'm going to delete that, add it to my output. 4 versus 5, 4 is smaller. 5 versus 7, 6 versus 7, 7 versus 9, 8 versus 9, and then we're out of items in one of them, and so we will add all the items from here, like if there was a 10, 11, we'd take all these items and add it to the end. There's no comparisons necessary to do because we're out of all the items. Everybody see how that works? We just simply add to the end of this list because if we're adding to the end, we're going to be bigger than all the items that have already been added. Okay? So we have list A, list B, linked. So list, I'm going to go ahead and call this integer out is equal to new linked list, just because we're dealing with linked lists. Return, and we're supposed to return a linked list, so I guess I got to put a linked list over here. Linked list integer is equal to new out new. Okay, and so return out. Now, what are we going to do? So while list A dot size is greater than 0 and Python, and list B dot size is greater than 0. While both of these are bigger, okay, we are going to do the following. Or really, you know a better way to do this? Oh, statement with empty body, of course, yes. That is the case. We're going to ask if list A dot get 0 is less than list B dot get 0. Okay? If list A is less than, if A's smallest value is smaller than B's smallest value, out, I'm going to do this in one line because we're at the point where we should be able to read these things. Out dot add list A dot remove 0. So if the front index of A is the smallest item, I'm going to remove it and add it to my output. Else, the one on the B side was smaller. And so I'm going to remove that one. What if they're equal? If they're equal, right, well, that's up for us to decide, and I'm just going to solve that by doing that. If they're equal, I'm going to consider the one on the left in list A to be quote-unquote smaller. Make sense? Doesn't really matter. If I had not put that equal there, it would have just been considering the one on list B to be smaller, right? In general, I try to avoid things with duplicates if the problem specifically deals with that. So now, however, we're almost done, but not quite, right? The issue is that one of these ones one of these is out of items and one of these does not have items, and we don't know which one that is. We could add a check over here, but honestly, it doesn't make sense to do that. We'll just do it. We could add a check over here saying if list A dot size equals 0, if list A is the one that's empty, then we do a loop to add everything from list B. We could do that. But honestly, it's just easier to do this. Out dot, and this is a fun method, add all list A out dot add all list B, and this is just to teach you that the add all exists. Add all takes everything from a collection and adds it to the other collection. And since one of these is empty, one of these is not going to do anything, right? And then the other one is just going to add all the items from there to the end. So just makes it a lot cleaner and easier to read and fit in one answer. Otherwise, you could just simply iterate through with a while loop saying while. The other way to do it is like while list A dot size is greater than or equal to is greater than 0. Out, and then you would just simply take this line and. So this is the other way to do it, which is you just have two while loops like this. One for list A and one for list B. Okay. So, as I mentioned last time, our next problem, and this is, like I said, O of n. Reverse I will come back to. In fact, depending on the amount of time, I might leave that as a quote-unquote exercise for the class. But as I mentioned, this one's an interview problem. Look it up. Please, for the love of God, look it up. Hint, hint, nudge, nudge, wink, wink. Look it up and look up the details of the interview problem where it gets reduced to doing it without any extra steps. Sorry, without any extra data structures. Okay. I will, but suffice to say, the easiest way to do it with additional data structures to add it is we do it just like we did the string one, which is you create a new linked list and then add everything to the head, and then there's your new linked list. Everything is in reverse, and then you just simply add all those to the end of your now empty original linked list. Okay. But I really want to work on this one because it's talking about a sorted linked list, and this is a question that deals with sorted linked lists. although not necessarily a class called sorted linked list, but it's a linked list that happens to be sorted. This might be, again, what we call a hint that you might be working with things that are sorted linked lists on your exam. All right, so I'm going to use a singly linked list over here because that's going to, on the exam, that's going to make things easier for me. I'm going to create a new class called sorted linked list. And I'm going to exit Zen mode for a second so that I can just go over here and I'm just going to copy the node class because I'm lazy. Also, if you do this, you'll notice we'll get some issues where it's going to, it tries to reference the other class. But there's our item. Okay, view, appearance. Okay. Okay, node next, sorted linked list. It's a linked list of E's. And then it's going to have a node E head. I'm going to also do a node E tail. And a size, int size, which initializes, and all these will initialize to null. That's or 0. That's fine. Now our task is, again, with these sorted linked lists, in case you didn't read through it, basically we don't have an add to a specific index here, right? We don't have it because it's a sorted linked list. It's going to keep things sorted. So if we have 1, 2, 5, and we call add 4, it's going to become 1, 2, 4, 5. It's not going to become 1, 2, 5, 4. It's going to find out, it's going to go through and figure out, okay, I need to put this into the linked list so it always stays sorted. Okay. It is either a doubly sync or singly linked list. You can use these to compare items. If you remember how to use compare to, you can do so for extra credit. I'm going to go ahead and do that. And I'm going to go ahead and enforce that. Extends comparable, but you wouldn't need to do this part over here specifically for the exam. I just have to do, again, this is part of the reason why we do this on paper, because you get to avoid things and assume things. But all this says is that it's going to assume that anything that is an E is not just an object, but it's a comparable object and has access to the compare to method. Okay. We cannot call the add int index. We cannot call the get node method, although you may rewrite it, although this is a hint that you do not need it. Your solution must run in O of n time, and I will typically attach a point value to that. On the exam, on a 15-point question, that's going to be 5 points, right? So if you cannot figure out how to do that if you have a solution and you're like, I know how to do this, if I had the get node method, which runs in O of n time, and checking each item, I could do that. And if you're running out of time on the exam, that might be the way to go, right? Rather get 10 points rather than 0, right? It's always better to go for points that you have, or you know you can get. So, public void add E. Public void add E item. So, now since I am kind of lost here, assuming I'm a student, I would fall back on what I know from doing my homework, which is that when I'm adding items or removing items, there were 5 cases I learned about. So let's go through those and see if those apply here and make sense here, right? First case was index out of bounds. Empty list. Adding head, adding tail, because if you're adding a new head or adding a new tail, then those change what the head or tail are, and thus the head and tails need to change appropriately, right? And then anything else. Okay. So let's go through those one at a time. First off, I recognize also this is an add method, so if I'm adding anything, I just need to make sure I'm going to remember to increase the size here. Okay. So index out of bounds. Because we are not specifically adding to an index, since we're not getting an index we have to check, right? We don't have to worry about this case. So we're done here, right? We are done with that one. And just put a dash to say we are done. Okay, we don't have to worry about it. We're done with that one. Empty list. We know how to handle that. That seems like a case I should handle. At the very least, I'll get some points for writing down this bit, right? Because if going from an empty list, that's technically sorted. It has nothing in it, so it's sorted. And then I add an item. One item is sorted, so okay, it's going to work for 0 and 1. So how do I know if it's empty? Well, if the size is currently equal to 0, right, that's how I know it's empty. And then adding that becomes pretty easy. First thing, if I'm going to be adding an item to a list, I do need to make a node. So to hold it, node E adding. Some people like to use new node or node, but because I'm on a computer and typing, it makes sense for me to just use more letters. New node item, just like that. Oh, I guess I need a constructor for this. That's again another reason why I do this on the computer. Sorry, why I do it on paper, because you wouldn't have to worry about, oh, what's the constructor? You just kind of assume it's there. Okay, public class, public node E item. This dot item is equal to item, right? There we go. So there we go. If size is equal to 0, this dot head is equal to the node that we are adding, and this dot tail is equal to the node we are adding. And we don't need to make this circular. It's not one of those circular linked lists, right? By default, the next the next node is going to be null, which is perfect, right? Doesn't need to go anywhere. Okay. So if size is equal to 0, great. Else, if adding a new head. Normally this would be put where we would put if index is, right, if index is equal to 0, right? That's normally what we would put here, right? That's how we would know for adding a new head. But we don't have an index, right? But we do have a value, and that's how we check if things are going to be a new where things are going to go. So how would I know if this item should be the new head? Well, if it's smaller than the current head, right? If it's smaller than the first item in the list, then it's smaller than everything in the list because the list is sorted. So if it's smaller than the first item, it's smaller than everything. So on an exam, again, you could write if item is less than head dot item. Remember, item is less than head dot item, not item is less than head. This would be a minor point penalty. This, on the other hand, annoys the hell out of me, where basically you try to do a comparison between the nodes. That doesn't work. You got to compare the items. Okay, the items and the things in the items and the things containing the items are different, right? The box containing your Amazon package and the item inside it are different things. Okay, this is going to error though because of course on the exam this is perfectly fine. I told you can do this on the exam, but because we are using objects, we can't use the less than greater than signs. Instead, what I have to do over here is say item dot compare to head dot item. And then I have to say if that is less than 0, right? And you know what? I'll say if it's less than 0 or equal to 0, right? If it's less than or the same, just to make my work simple, right? If it's, you know what? I'm going to assume that there's no duplicates, but I'm going to assume there's no duplicates, and then we can go back in and add it check for duplicates later, okay? So less than, so if it's smaller than the smallest thing, great. Okay, right now I'm going to assume no duplicates, and then I'm going to figure out if that's something I have to worry about. If that's the case, adding dot next is equal to head, right? Attach our new node to the list, and then update the reality of the list to compensate for this. Right? That's it. That's all we have to do to attach that item. And now that we have this, adding to the tail is actually pretty much the same thing, right? We just got to take this and we're just going to adjust a few things, right? So we're going to compare it to the tail, and it would be the new tail if it's bigger than everything else, right? If the item is bigger than the item in the tail, and we can just simply go to the tail directly because I'm going to keep track of that. So if it's bigger than the tail directly, boom, that's a new tail. So that changes up what we do here a bit, which is we say, hey, tail.next, instead of pointing to null, it's going to point to the new item. And then that is going to be the new, and then the new item is going to become the tail. But does this make sense to everybody so far? It's probably making a lot more sense now that I'm just walking through it. But this is the key when we're dealing with these kind of issues, that we want to stick to what we know, right? Always fall back, if you can, onto familiar knowledge. The everything else is where we fall back and where we hit some unfamiliar knowledge, but we're going to get there, okay? And we're going to take advantage of what we know from our assumptions. All right. So if it's anything else, we do know a big fact that's going to help us. We know essentially that the item is going to be between the smallest and the largest item, okay? And so we could technically do so we have a few ways of doing this. We're going to need to iterate through, though, to find the item. But we know it's going to be in between. So first things first. Node E current is equal to head, right? To go through. And then we're going to do a while loop. And this while, what we put in here, it just matters that it keeps going. I could do this while true, or while not done, which is what I would prefer to do, as opposed to breaking. So I'm just going to do a while not done. We could do a current dot next is equal to head. Oh, sorry, while current dot next is not equal to null here, but we're never going to really end here. Why don't we just do that? Current dot, and we'll figure that out as we go. It's not equal to null. Now, because what we're going to do is that, yeah, let me explain here. We know that because we've already done this comparison, we know that the item we are adding is bigger than the first item. It's bigger than what we're currently at, right? Make sense? Right? Suppose so we're somewhere in this list. Just happens to be the first location. But we know that we're looking at this. We have our current, okay? We have our current dot next, okay? And then we have the item that we are currently trying to add, right? And we know that basically that we're going to look for a position where item can kind of fit between these two, because it's got to fit between the two. It's bigger than the smallest thing and smaller than the biggest thing. So it's got to fit in between these two somewhere. So we're going to find a position where basically item is smaller than current dot next item. So that's why we got to check to make sure that current dot next is not equal to null, because if current dot next was equal to null, we would not, this following comparison would not work. If current dot next dot item. So let's go ahead and see if item, and I'll reformat this as a compare to statement in a second. If the item is less than current dot next dot item, well, we know we're bigger than current because we just checked current. We know we're bigger than current, but we're less than item. We know we're bigger than current, but we know we're less than current dot next dot item. That means we fit if this comes up true. So we would say we would say adding dot next is equal to current dot next, right? So we would put this right like that, and then we basically have to erase this and make it point over and do that, right? That classic linked list add, which is saying current dot next is equal to adding. Current is equal to current dot next. So this is where we run into some of the issues, I think, right? Because logically this does work, but then I have to, if I want it to stop, I have to put a break in over here, which is part of the reason I was talking about, okay, we should probably just, why I'm probably just going to do this. And if you've not seen this before, I love the way this looks. Boolean done is equal to false, right? We're not done. While not done, do this. And then when we do the thing we want to be done, we set done equal to true, and then we'll stop, right? Make sense? Very kind of syntactically nice way to look at things. And now finally, let's just go ahead and fix this, dot compare to, right? And if you do the compare tos, that's extra credit. Less than 0. Okay. And yeah, if we want it to be, and this will work. This is great. If we wanted to consider duplicates, just change those greater thans and less thans to greater than or equal to's, and that will actually take care of everything you need. And I'll leave that as a exercise for you guys because we are getting close to time. So because we are getting close to time, I do want to, I will again give you a hint about this. This is on the exam. It is a Parsons puzzle, but a version of this is on the exam. I will be giving you a version of this that I've come up with, but I'm giving it to you as a Parsons puzzle. So I'm giving you all the code here, and a Parsons puzzle basically says, I gave you the code, but it's all scrambled up. You got to unscramble it, essentially. So all the lines are there. They're just out of order. Make sense? It's a 5-point problem on the exam. So that should give you some intel that I think is appropriate for this because I don't want to go back and make an additional video on that one. All right, analysis. This is the most important one, so please stay even if we go over time. Okay, this is very important. You know this is going to be on the exam. Lists can be implemented in a number of ways. Compare and contrast a linked list to an array list. In which situation would you like to implement one over the other? Okay. So let me go ahead and just kind of talk about this. There's a couple different ways we want to implement linked lists versus array lists, right? So the first is memory. That we haven't really talked about this, but basically both the linked list and the array list, basically they use memory in different ways. with a linked list, with an array list, right, what we do is that we have basically an underlying array, and basically the used area is our size, but the whole array has a capacity, right? And so we have all this unused space over here potentially, right? So with an array list, there's a bunch of there's unused space, potentially a bunch of unused space, a bunch of unused items. Now, what does that mean? Well, first off, how much is there? If there's n slot, so how much is there? If the size of the list is n, what is the maximum this could be? And the answer is this could potentially be n unused space. Why is that? Because every time we reallocate, we double the size of the list. So technically n minus 1, because you reallocate, then you add. Okay? So if you need to, if your array list gets all the way full up, what we do is we say, that's no good. We are going to create a new list with twice the capacity, and then copy everything over, and then add that item over. So this could potentially use O of n, it could use O of n extra empty slots. Now, what is a slot in this case? A slot is basically an int. It's a memory location. Okay, it's a memory location. It's a reference to the other item. The array list actually doesn't store the items. It stores the references to the item that are just floating around in memory. So your array list, your array actually looks like kind of like this. Make sense? But the structure doesn't make it easy to kind of look for. Okay, linked lists. How do those waste memory? Well, you don't use up extra slots. You create those slots as you need them, right? That doesn't mean there isn't any overhead, though, right? Each of these slots, contains basically one 1 inch worth of memory overhead, which is perfectly fine. But over here, we have the item, which is basically the equivalent to the slot in the previous one. Then you also have the next and the previous. So this uses basically, for every item, you have basically 3 ints worth of overhead. Is that a question?
Yeah. Is it relevant that the fact that like in array list, the only addresses are next to each other while like in linked list they're like scattered?
Not really. No. That's just going to a location is assumed to be constant time. It's just a matter of getting to that location in the first place when you're iterating through. Yes.
So does an array list use more memory?
It depends. It depends, really. Because over here, you could have a bunch of wasted space that's just not being used. Here, we have we have extra overhead, but that space is being actively used to do stuff, if that makes sense. Right? So here we have basically n pointers worth of overhead. Okay? So linked lists have extra overhead. If I were to succinctly say it, I would say array lists can waste O of n space. Linked lists use O of n extra overhead for the next and previous references. Make sense? Kind of keying it differently, but they both use O of n extra space. You just got to be aware of how you do that. For instance, and this starts getting into things I would consider above the ordinary. You could use, I think it's clear to completely remove an array list, but you can also use trim, which creates a new array that's exactly equal to whose capacity is exactly equal to the current size, meaning there's no wasted space. You can also set up array lists to have exactly the amount of space that you need initialized. most students get 4 or 5. That's a 5-point part of this. Most students get 4 or 5, assuming they don't, you know, make stuff up. This next part which is checking against add and remove, comparing and contrasting the add remove. This is where a lot of students mess up. It's worth 8 points. So let's go over linked list because that is the easier part. Linked lists are fairly straightforward. They are constant time to add to the head or tail because you know where those are. But they're O of n for anything else because you have to, now the big O cheat sheet will say it's constant time to add, but it's constant time to add plus the amount of time it takes to seek to that location. If you want to add to like index 10, you have to go to index 10, which takes 10 steps. If you want to go to you add something to index 50, you have to go to index 50 and add something there. Okay? So, but adding to the head or tail, which is the most common places to add items, constant time. Now, for an array list to add, right? Basically, when we're adding or removing, we care about 3. And by the way, this is true for adding or removing for a linked list. Okay. For array lists, we care about 3 locations, right? Same locations that we cared about for the linked list. Beginning, ending, middle. Let's go through the beginning and endings beginnings and middles because those are the same. Adding to the beginning or moving from the beginning, you have to shift over all the items, right? You've learned about how all the items in an array list have to shift. Doesn't matter if you're adding or removing. Middle. Same deal. You're just shifting half the items now, but you're still having to shift. Adding to the end, though, well, that becomes just big question marks as to adding to the end. AL adding to end is actually probably the most complicated part of this. The most complicated part of this 20-point question. Okay? Because removing, no problem. That's actually constant time to remove from the end, right? Removing from the end, constant time, don't have to worry about it, right? Nothing gets shifted. Adding to the end, however, right, is constant time except if you have to reallocate. And that's where most of our students lose points, where they forget to mention if you are having to add, if you add to the end of an array list, you have either a constant time add or you have to reallocate. Make sense? So to briefly, adding or removing to an array list is linear time, O of n time, except when you're adding to the end or adding or removing to the end, where it is constant time, except if you have to reallocate, in which case it's O of n again, right? So O of n except constant except linear. Make sense? Overall, if you were to compare and contrast and say which one is the better for adding and removing, I'd say linked lists because you can just add and move to the end constant time all day. If you know a specific location in the middle where you just have to add everything, you find it once and you can keep adding there. And then finally, get set, right? Get / set, so changing the items. This one's super easy, super duper easy, easiest 7 points you should get. So please don't mess this up. I saw a number of students last year who messed this up. Okay, array lists. Array lists use are constant time. They use arrays, which you can find an index of an array and just simply get there, no problem, instantly. Okay, there's a memory formula. I believe I talk about it in the lecture videos. If not, then email me. It's not, you don't need to know that for the exam, but it's pretty nifty. Linked lists, you have to manually go there. That's O of n always. Array lists, constant time, linked lists, linear time for get set. Okay, that is it. So that is it. Good luck on your exam tomorrow. I will upload this. Sorry, I've got a lot. I know a lot of you have to get to class. If you have additional questions, though, please feel free to ask me as I make my way to, my room.